our next goal is going to be to cover the extreme value theorem. But before we get to the extreme value theorem, we need some terminology. So we're going to start with a couple definitions. Definition, we're going to take this function, and I marked off a few points on this function. It goes through the origin. I've marked off 2, 4, and 6 on the x-axis, 1, 3, and 5 on the y-axis. This point up here is 2, 3. This point down here is 4, 1. This point up here is 6, 5. That's why I have those dotted lines there to make it clear that is 6, 5. And then 2, 3, 1, and 4, 1. But what we're going to do, we're going to consider that function just on the interval, the closed interval, 0 to 6. So we're only looking at the x-axis values between and including 0 and 6. So we're only looking at a piece of the function. I'm just going to shade it in. We're not looking at the entire function. We're just looking at this piece of the function starting at this point down here, 0, 0, ending at 6, 5. We're only looking at that piece, and we're going to use that to define 4 words. We say f of x has absolute maximum. Given this interval, the absolute maximum is going to be the largest y value it hits, and it's going to occur at a certain x value. F has absolute maximum. In this case, the largest y value just on the interval 0 to 6 is 5. So we call that the absolute maximum. 5, and we'll also say when it occurs at x equals 6. An absolute maximum and these other 3 words are going to be y values which occur at x values. Similarly, we say f has absolute minimum. That'll be the lowest a function gets on this interval. The lowest it gets, down here, it goes down to 0. The lowest value on 0 to 6 it hits is 0, and it occurs when x equals 0. I guess these should technically be commas. Whatever. We'll leave them as periods. We say for all of these, I guess. Now, we have this notion of absolute maximum, absolute minimum. Those are the largest and smallest the values get, the y values get. We also are going to define one other type of maximum or minimum called a local maximum or minimum. Absolute you may see called global. Local you may see called relative. You may see You may see this called a relative minimum instead of a local minimum. I'm going to use local. I like the word local more. It actually means a little more in math than relative. But we say f has a local maximum. Well, what's a local maximum going to be? A local maximum is going to be a point like this. More on this in a moment. But for now, let's just say a local maximum is going to look like this. It's a point where the y value is higher than all other y values close to it. So here, up here, is going to give us a local maximum. It's the top of a mound, let's say. Local maximum, what's the y value at that top? The y value at the top of that is 3. And that occurs when x equals 2. Similarly, a local minimum is going to be the bottom of a mound, like that. Point down there at 4, 1, and that local minimum will be 1 when x equals 4. Now, I'm going to introduce a little more language with these absolute maximum, absolute minimum before talking more about local maximum and minimum. If we considered all of 0 to infinity on, let's just say 0 to infinity. 0 to infinity, so including, that thing keeps going up. It may be tempting to say it has absolute maximum infinity because it keeps going up. But we'll just say on 0 to infinity, we say f has no absolute maximum. So, we're not going to say it has absolute maximum infinity. We'll just say if that is the case, it has no absolute maximum. Our absolute maximum, minimum, and local ones are going to be finite values. Now, a little bit more on the word local. This will be another remark. Local in math means we look only at the values close to the values we're considering. We're looking. So back in week 4 or 3, in one of the workshops, we did the more formal definition of the limit. Local technically uses that. I'm trying to phrase it in a way that goes around that. Means we look near a given x value. I'll put near in quotes because local and near kind of go together. So in this example, in not the first, a new example, in an example like this, 3, 5, f has a local maximum of 5 because 5 is the largest y value near 3. So what we're really doing in a graph when we say local is, we're going to only look close to 3. And if we look only close to 3, that's going to correspond to a chunk of the graph going close to this point. So a local maximum means it's the maximum nearby. So it may not be an absolute maximum as we saw in the first example. In this second example, that is a local maximum. It's also an absolute maximum. If I put arrows like that, it is also an absolute maximum. So I'll also note, I don't have room to write it under there, so I would like to write this under here. I'll just say also f has absolute maximum 5 when x equals 3. So in that case, absolute maximum on the entire real line. But this example illustrates that a local maximum could be an absolute maximum as well. And an absolute maximum could be a local maximum as well. In that first example, they were all different, but here, the largest y value also corresponds to the largest y value nearby. And in that first example, that was not the case. So let's next look a little more into where a local maximum may occur. And we're going to do that by looking at a couple graphs. Let's just see how I drew them here, because I like how I did them here. Here. Notice. Well, I'm going to draw 4 graphs and then I'm going to say notice. Local maximum, local minimum means largest nearby. Well, we have 4 different graphs on which one of them may occur. It could look like this. 3, 3 boards, 4 graphs. Well, okay, let's do it like this. It could look like this. In the first case over there, we would have a local maximum. We're not considering right now absolute yet. Right here, we're just looking at local maximum. Maybe I'll just mark off the point. I don't care necessarily about the x and y values yet. So in that first one, we have that local maximum. This one, we have a local minimum. Here, we also have a local maximum. So in that case, it's rounded off. Here, it reaches a point. And down here, or in this next one, that's a point at the bottom. We could have a local minimum that looks like that. And we're going to observe a local extreme point. Words we haven't defined it. An extreme point just means maximum or minimum. In this case, local. A local extreme point. Maybe I'll just say I'll define it since we didn't define it. Max or min. Maximum or minimum point will occur where? Well, we have these 4 graphs. We're in a calculus class. Can we describe what happens here using calculus? Let's start here. Do we know anything about the derivative at that point? Do we know anything about the derivative at that point? Do we know anything about the derivative at that point? Do we know anything about the derivative at that point? Well, we actually know a lot about the derivatives at all 4 of those points. So a local extreme point will occur at a point, at an x value, where what? Well, what's the derivative here? Slope of that line is 0. Slope of that line is 0. So those first 2 will occur at a point where f prime equals 0. What about those other 2? Well, we have a corner point in both cases. Here we have like a top corner point. Here we have a bottom corner point. What do we know about the derivative at corner points? Well, how do slopes of tangent lines change? Well, look at slopes of tangent lines on the left of that point. They're all positive slopes. Slopes of tangent lines on the right of that point. They're all negative slopes. Positive slopes, negative slopes. Similarly, over there we'd have negative and then positive. Well, that means that the limit on the left will not, the limit which defines the derivative on the left will not equal the limit which defines the derivative on the right. Meaning the derivative is undefined in these 2 cases. And similarly, if you had, a cusp, you could have a local maximum. We won't worry about vertical tangents. But here, with these 4 graphs, we see that we can easily, using the derivative, describe where a local extreme value will occur. So let's define this. Definition. We call an x value I'll be a little informal, such that f prime of x equals 0 or f prime of x is undefined. A critical, let's spell critical correctly, a critical point. We call an x value such that the derivative is 0 or is undefined a critical point. And we can see from this observation above that being able to describe these in the same breath may be useful. Right here, this observation could now be rephrased. Observe a local extreme point will occur at a critical point. So let's just do an example. Find the critical points. Example, find the critical points for this function f of x equals negative x squared plus 3x minus 2. Find the critical points. Well, we need critical points are where the derivative is 0 or the derivative is undefined. So f prime of x, we need, it's negative 2x plus 3. Well, that's never undefined. Where is it 0? When x equals 3/2. So in this case, we have one critical point. There is only one in that case. Next, do I want to state the theorem or not? What do I want to do next? I'm debating. Well, let's debate while I erase. Debate has been settled. Let's consider two more graphs. So with that previous discussion with those four graphs, we covered a little bit about a local maximum and a local minimum. Let's talk now a little more about the absolute maximum and absolute minimum. And let's do that for these two examples. So here, let's mark this off A. Let's mark this off B. I'm going to write a sentence or two underneath it. And here, this will be F. I'm just going to call both of them F. Let's call this B. Let's call that A. Let's mark off that point. Mark off that point. Let's just call that F also. I'm going to close that off for this example. It may be useful if you look through your notes later to note that I have closed them off, because that'll be consistent with the extreme value theorem. But where do the absolute maximum and absolute minimum on A to B occur? So on the closed interval A to B, the absolute, so now we're not concerned with local. We're looking at the absolute maximum occurs at, now I'm not too concerned with the actual value, but let's shade in A to B a little. A to B. Well, where's the absolute maximum on A to B? Up here. The largest y value is up here. So it occurs at B, but less specifically, it occurs at an endpoint. And what about the absolute minimum? where does the absolute minimum on A to B occur? Well, it's down here. It occurs at a critical point, but I'm just going to say it occurs at a point. It occurs down here. Derivative down there is 0. So I'll just say where f prime equals 0. Well, that is a useful observation. Maximum occurs at an endpoint of the interval in consideration. The absolute minimum occurs at a point where the derivative is 0. What about in this next graph? Well, again, we're going to look at A to B. On A to B, the absolute maximum, abbreviation abs max, occurs where? Where's the largest y value? Well, the largest y value is now up here at a corner. So it occurs at a point where f prime is undefined. And the absolute minimum occurs at, well, where does the absolute minimum, where's the smallest? We're only looking at A to B again, remember. The smallest y value is here, occurring at x equals a. So in less generality, well, in more generality, I should say, the absolute minimum occurs at an endpoint. Well, those are some useful observations. Notice if we didn't close off the intervals, if we took an open interval in this second one, there would not have been an absolute minimum. In this first one, if we left the intervals opened, meaning open interval A to B, circles on these points, instead of filled in dots. Well, if we did that, this first one would not have had an absolute maximum. There would not have been a largest y value if we did that. But let's now state the extreme value theorem with all of this in mind, because I haven't stated anything about it yet. Although I hinted at the result by using the word the after using that prepositional phrase. If f of x is continuous on I use a different letter in this in my notes. I'm just going to not use that. If f of x is continuous on A to B, then all we need is a continuous function. Then f of x attains an absolute maximum and an absolute minimum somewhere on the interval A to B, possibly including endpoints. If f is continuous, then it definitely has a largest value and a smallest value if we're looking at the interval, closed interval, A to B. So how would we go about, our goal is going to be to find these values. How would we go about doing this? Well, where did I write it? We combine our observations from, really from the last, those two examples, plus the 4 describing local maximum, local minimum. So let's say combining our observations and examples, we see to find absolute max and absolute minimum. Well, there are a few different things we need to do. I should specify of f of x on a to b. First, well, we see over here that it could, an absolute maximum or an absolute minimum, could occur at a point where the derivative is 0, or it could occur where the derivative is undefined. So we have to find the critical points. Find the critical points. So remember, that's where f prime equals 0 or is undefined. Well, that's one thing we have to do. What else would we have to do? Well, we saw in these examples that an absolute maximum or an absolute minimum could occur at an endpoint. So 2, find endpoints. And what are they? A and B. Well, and then what do we have to do? Well, we saw that an absolute maximum or an absolute minimum will occur at either endpoints or points at the bottom of mounds or top of mounds or bottom of points, tops of points. But to figure out which one is a maximum, which one is a minimum, what we'll do is find all of the corresponding y values and compare. So I'll say compare f evaluated at all such points. The largest will be the maximum, absolute, and the smallest will be the minimum. Notice we are looking at a closed interval, a to b. If we took an open interval, there wouldn't necessarily be an absolute maximum or an absolute minimum. You know, for example, up here, if this were open, there wouldn't be a largest value. Pick a largest value, well, you could always get larger. In that case, there would be no absolute maximum. But if it's closed, there will be. So let's look at a few examples. Find the absolute maximum and absolute minimum values and where they occur for f of x on the given interval. So notice we're going to have y values and x values as part of our answer. The maximum minimum values are y values. Where they occur at x values. So we have 3 examples here. The first one, f of x negative x squared plus 3x minus 2. We already saw that example before, so you could just go back to that to find the critical points. 3 has, but I'll show the entire work here. So following our 3 steps, we needed what? We needed critical points, we needed endpoints, and we compared the function at all those values. Well, so f prime of x here, negative 2x plus 3 equals 0 when x equals 3 halves, never undefined. So we have 3 halves, and our 2 endpoints here are 0 and 2. So we know from that, on 0 to 2, an absolute minimum will occur at one of these points. An absolute maximum will occur at one of these points. We just have to find which. So let's compare the function at all these values. F of 0, negative 2. F of 3 halves is what? So we have negative 3 halves squared, negative 9 fourths, plus 9 halves minus 2. So what is this? Well, 9 halves minus 9 fourths is 9 fourths. So we have 9 fourths minus 2, which is what? 1/4. F of 2, well, negative 2 squared, so negative 4 plus 6 minus 2, which is 0. I guess that does factor. So here we have all of our points. So we'll write I'll write the conclusion. I guess I would usually do like I'll do it like this. It's not a bad curly brace. I'm usually pretty bad at drawing the right curly brace. That one's one of my better ones. The left one I can draw semi-capably for some reason. But the right one I've always had trouble with. But what are we doing here? We need the largest value and the smallest value. So f of x has absolute maximum. The largest value is a quarter when x equals 3/2, and it has absolute minimum. The smallest, -2, when x equals 0. So we found our critical points, we found our endpoints, we compared the function, evaluated all of them. The largest is the maximum, the smallest is the minimum on this interval. Remember, we are just looking at a closed and bounded interval. Bounded meaning it doesn't go off to infinity. B. Well, again, we need f prime. What's f prime here? Well, we have a function squared. Derivative of a function squared is 2 of them to the first times derivative of, in this case, x minus x squared. So 1 minus 2x. And we want to set this equal to 0. I would really like to leave this sentence here so I don't have to write it 3 times, but I guess I'll just write it 3 times. I'll have to get over it. We want to set this equal to 0. When is this 0? I guess I could have factored it a little more. Maybe I'll factor it a little more and then set it equal to 0. What does this equal? Well, it equals 2x times 1 minus x times 1 minus 2x. Maybe I'll make that a little bigger. Pull out an x from those. 2x times 1 minus x times 1 minus 2x. When does this equal 0? It equals 0 when x equals 0, x equals 1, or x equals, what, half. Well, okay, we have all those points. What's our interval? -1 to 1. That's a pain. That's a lot of values. But that's okay, I chose the example. -1 to 1, with those values inside of it, gives us what? Our 4 points to consider are -1, 0, half, and 1. I always like writing them in order. I don't know why. We need to consider... Oh, also, that's never undefined, because it's just a polynomial. F at -1, f at 0, f at a half, f at 1. Notice one of them is the same as the endpoint, which is a little convenient. Where's our function? Down here. F at -1, -1 minus 1, -2, all squared is 4. F at 0, 0. F at 1 is also 0. F at 1/2 is what? A half minus a quarter, all squared, which is 1/16. Then you take a step back, look at the computations, and make sure you didn't overlook a number or something. So -1 minus 1 squared, yeah. 0, the other one's 0. Half minus a quarter, all squared, is a 16th. Okay. Well, now we need the largest and the smallest. So f has absolute maximum. Largest is 4 when x equals -1, and absolute minimum. Notice here the smallest value occurs twice. Well, that can happen. That's okay. Absolute minimum 0. when x equals 0, and it also occurs when x equals 1. So an absolute minimum could occur twice. You know, just take it, maybe I'll side remark. This isn't what this function looks like, but, you know, if you just take f of x equals x squared on, you know, negative 2 to 2, for this function on negative 2 to 2, the absolute maximum occurs twice. So an absolute maximum or an absolute minimum could occur twice, but notice, of course, you know, it's the highest value, so the y value is going to be the same. On negative 2 to 2, the absolute maximum of x squared is 4, occurring at 2 and negative 2. The minimum is 0, occurring at 0, which you could show using calculus. The critical point there would be 0. Or you could show using that graph for an example like that. And let's look at this last example. So in those first two, the derivative was undefined nowhere, but here the derivative will be undefined somewhere. So let's see. Part C, f prime of x, derivative of x is 1, derivative of 1 over x to negative 2, also known as negative 1 over x squared. Well, we want to set this equal to 0 and find where it's undefined, but I'd like to first write this as one fraction. Why would I like to do that? Well, we're looking for where this is 0 and where it's undefined. Where this is 0, where it's undefined, when it's written in its fractional form, reduces to finding where the top is 0 and finding where the bottom is 0. So I do like writing it as a fraction because of that. But the top equals 0 when x equals positive or negative 1. You know, you could factor that x plus 1, x minus 1, or you can add 1 and then square root. Either way, you get positive, negative 1. And is undefined. When is it undefined? When x equals 0. Well, okay. So we found our critical points. Positive, negative 1, 0. So we take our critical points, we take our endpoints, we compare the function. F of 1, that's the easiest one here. F of 1 is 2. What's f of 1/5? F of 1/5 is a fifth plus 5. And you could write that as 26/5 if you want. What's f of 4? F of 4 is 4 plus a quarter. So the largest is the maximum, the smallest is the minimum. So f of x has absolute maximum. What's the largest? Well, if I wrote this as 26/5 and wrote this as 17/4, I'd have to do extra thinking to figure out which is larger, which is smaller. But when it's written like this, you know, this one is obviously larger than that one. So the absolute maximum is, in fact, 26/5 when x equals 1/5. And absolute minimum, smallest, is 2 when x equals 4. So in all of these, we had a largest value, we had a smallest value. So do practice these computations. There will almost definitely be one like this on the next, well, there will definitely be one on the next test. And almost definitely there will be one on the final. I would lean more toward definitely than not definitely. So do practice these, and also do note, we didn't have to consider 0 and negative 1, because our interval doesn't care about 0 and negative 1.